Good morning, everybody. My name is Graeme Smith. I'm the Business Development Manager for Africa and Eurasia, and we're going to talk today about design and optimization of spiral beneficiation plants. So firstly, what are spirals? It's a process equipment with no moving parts used to separate valuable minerals from non-valuable, and typically with a top size of -1. We're going to take a short clip and actually see this in action. As we can see in the video, we are running here chrome on the inside of the spiral, concentrating to the concentrate outlet. We have our middling fraction as we start adjusting the cutter there to pull more heavy concentrate to the inside, and obviously our lights and our silica moving out towards the outside of the spiral. This was a cleaning application, and this produced very good results for us with this client in their test work. So after seeing that, who actually uses this in industry? It's the chrome industry, heavy minerals, coal, tin, tantalite, copper, gold, iron ore, and the list is growing every day as new commodities come onto the market. So when we as a team start looking at your flow sheet and how we can actually optimize it, there are a few criteria that we actually start to look at. The first is plant head grade. Are you running a chrome plant with, say, 5 to 35% head grade, or tin? Maybe iron ore, 25 to 40%. The second part of that is, where do you want to go? Are we going to try and get you to a sellable product, maybe a 46% in chrome, or just 40%? Maybe tin, only 30, or maybe as high as 60. It all depends on where you want to go. The third factor we start to look at is your PSD and a size by assay. And as you can see from this graph, this client had a PSD with a P80 of 105 micron. This factor helps us to determine exactly where your gangue minerals are and where we can actually optimize it and bring in the most valuable mineral into the circuit. The fourth is the associated minerals that go along with it. On the left, what looks like just chrome and silica, there's actually a third, olivine, a semi-paramagnetic mineral which moves together with the chrome. Or on the right, we have copper malachite with hematite associated with it. Fifth, we start to look at what's going to follow your spiral plant. On the left, we have a WIMS. Could be in your iron ore circuit, where you want to remove that last bit of silica or do that final concentration upgrade in your hematite. Or on the right, a shaking table. Maybe you've only taken 30% tin and used tables to concentrate that up to your 60%. The sixth portion of it is our spiral selection. And as you've heard before me with Referenza and Laisi, we are gaining new spirals every year. And as you can see from our selection, we have a huge number to do with heavy minerals, as well as 3 within our coal industry. This helps us to do the selection of producing the right circuit for you with the right spiral. So when we start looking at the flow sheet evolution, we have here a 4-stage plant, which was used in the copper industry, where we have taken a 2% copper and concentrated that to 15%, which was in this case a sellable for this client. Here we see it actually being installed, a small 15-ton per hour plant up in Zambia. As the circuit evolves, we start to add on to that. And as you can see here, we've added a magnet, which is preluding the first 4 stages of spirals. Here we removed magnetite and then sent that concentrate to a final cleaning stage. By removing that iron, we're allowing the chrome and silica in that final cleaning stage to separate and produce a 50+% chrome. As you can see it here, this has actually set up that circuit up in Zimbabwe, producing an alluvial chrome concentrate. We go to the extreme now, where we have a 28-stage spiral plant with a height of 46 meters and almost equivalent foot floor base along the bottom. This is a small 600-ton per hour chrome plant out in South Africa. We go to the opposite extreme now in very remote locations. This is 2 20-ton per hour spiral plant test plants set up in the Congo for tantalite. This has been used as a bulk reduction rather than a concentrator, feeding 20 tons per hour to each unit and then feeding 4 tons per hour to the shaking tables. concentrating from 0.03 kilograms per ton to 4.5 kilograms per ton. The last and the final step is test work, and this is the most important and crucial step in this circuit. This is where we take these previous criteria and we actually put it into practice in our R&D facility. Here what we have done is we have taken an existing circuit which was 4 stages, worked through the criteria, and have proposed a 9-stage circuit for the client. Now what does that really mean to you? If we look at it, we had a head grade of 22% chrome in the feed. We produced a final concentrate of 40% with a 26% mass yield, as can be seen. After running the test work, we managed to increase that mass yield by just over 8% to 34.5% with a chrome concentrate of 41%. Now this is all good and well, but what does that really mean to you? Let's have a look at that. Let's assume a 100-ton per hour feed to the plant. You operate at 624 hours in the month, and today is selling that concentrate at $150 per ton. That upgrade costing you $500,000. Seems a lot, but let's look at the numbers. The 4-stage mass yields you 16,500 tons with a revenue of just under $2.4 million. The 9-stage, however, has a real nice increase to 21,500 tons, producing a revenue of $3.2 million, meaning that $500,000 investment is paid back to you within less than 1 month. So in concluding, spirals are actually very simple. They're used in a variety of mineral applications, as we've seen earlier. There is a large selection of spirals to choose from to get to the right application for you. We have high throughputs in very, very small footprints. You then can start to look at things like gravity feeding or pump feeding, which is going to suit your application. And existing circuits can be optimized through test work to deliver the results you're looking for. Thank you.